take a look at a general function and consider its integral. Okay, so we were looking at from a to b, and we know that the integral is the area under the curve. So here's an interesting question. Is there a rectangle that we can construct that has the same area as the integral? Now, if you start with the rectangle, let's say down here, it's simply going to be too small because, there's the area under the curve greater than that. If you come up high, it's going to be too big because there's going to be a piece missing. So you need something kind of in the middle, perhaps something close to this. And the idea is that the rectangle has the same area as the integral. Now, I may not have drawn it precisely. The point here is that there is one. Okay, so we have this function f, and what is this? Like, what is the height of the rectangle? Interestingly, there are 2 points on the curve, and we could call one of those points C, and the point is that there exists one of those such that this height is f of c. Okay, so what we have now is we've got f of c, the height of the rectangle, times b minus a. Okay, so that's the area of the rectangle, and that equals the integral from a to b of f dx. Now, the fact that such a c exists between a and b, right here we have 2 possibilities. If you like, we could say it's this one, is the mean value theorem for integrals. Again, you can imagine, right, if you have a rectangle down here and you gradually move it up, that's going to be too high, that's too low. Eventually, because the real numbers, are infinitely dense, that you can find a precise rectangle that does this. And there's even additional interpretation to this. So you can also say f of c equals 1 over b minus a, integral from a to b f dx. Oops. And when you do that, it's saying the same thing, and it is suggestive though. And what's suggestive about it is that it's called its own thing. Okay. You're taking an integral, okay, area under the curve, you're summing it all, but you're dividing by b minus a, and that's actually the average of the function. Now, why is this the average? Like how is that the average? You could think about something like this. If you wanted to get generally an average, right, like the mean, the mean is something like this. So for the mean, you would say, okay, I'm going to add up all my different terms, and who knows how many you have, but then you're going to divide by each of those individual terms. So you could think of this function as being that, right? You pick some different points on the function, and you divide by the number. Well, as you get more and more terms, right, n becomes sort of larger and larger, and then you end up taking more and more values. You can take a limit, and goes to infinity, and in effect, you end up with not finite terms, but you end up with the integral, and it's not like n, it's simply this interval b minus a. So in calculus, if you are ever asked for the average of a function, you simply take the integral and divide by b minus a. Okay? If you like, we could do a basic example. So we could say, example, average of x squared from 0 to 4. Okay, so the idea here is what we want to do is figure out the integral divided by 1 over b minus a, which in this case is 1/4. And so the f average here is equal to 1/4 And then I just go from 0 to 4 of x squared dx. And we can compute this. Here we go. It's 1/4. The function becomes x cubed over 3. And it's evaluated at 4 and 0. And that's going to be 16/3 because one of the 4's will cancel out. Okay, so that's the average value of the function. Note that 4 squared is 16, 0 squared is 0, and it is in fact in the middle. Okay, so what we're going to do next is we're going to look at a sort of a general example, and we're going to look at some other integral interpretations with it. So consider the following. Let's consider that we have some different times. Okay. Say 0. Now the times might vary. Okay, let's say that we've got 10 here, 20, then 40, 70. Okay, maybe even 90. And then we have different values, and the values could be something like gallons, okay? So how many gallons do we have at each of these points? Let's say we've got 100, 200, and then we've got 250, 300, 400, and we end at 500. Okay, and so we're going to ask a series of questions about this. Okay, so this is some particular function, and we'll just call it a function f. And what it does is it measures the number of gallons at a certain amount of time. Okay, so the first thing we're going to do is estimate f prime of 30. Okay, and so now let's talk about what this means. Okay, so suddenly this is not an integral question, this is a derivative question. The question is, what is the rate of change at 30 seconds? Okay, when you have a table, you can't actually, how do I put it? You can't get the exact derivative, so you have to approximate. And so this is going to be the classic, well, 30 would be in the middle, and so we can go in between them and approximate to say, okay, well, I don't know what f of 30 is, f prime of 30, but I can approximate it. It's f of 40 minus f of 30 all over 40 minus 30. Okay, so this is just using the general slope formula, kind of like the pre-calculus slope formula. You find a point in the middle, it starts f of 40 minus f of 20 over 40 minus 20, and then we just plug in the values we have. Okay, well that's 40 minus 20 is 20, which is the denominator. The numerator here would be 50, so it's 50 over 20, which is 5/2. Okay, so that is how we would estimate f prime of 30. Question B. We want to know next, evaluate, okay, the integral from 0 to 90 of f prime of t. Okay, as to be with dt since we're in t's. Okay, so this is a different question, note the difference, and it's asking us to integrate a derivative. Well, the fundamental theorem of calculus tells us that, well, look, if you want to integrate a derivative, that's the actual function, okay? And additionally, what you would say is it's the function at the endpoints, right? So if you think about it like this, here's some function, you're supposed to take the antiderivative of that function. Well, the antiderivative of f prime of t is simply f of t, okay? And you evaluate it at these 2 points. So it's f of 90 minus f of 0. And we just go to our table and look, well, that's 500 minus 100, and that's simply 400. Okay? And so that's kind of interesting, and what is it actually telling us? It's kind of interesting. it tells us, I mean, if you look at it, it tells us the difference, in volume of the number of gallons that have accumulated, right? We start with 100, we end up with 500, 400 additional gallons have accumulated, but then you can interpret it in the context of this integral saying, hey, let's sum, over time, so the first 90 seconds, the rate of change, right? The rate of change of how many gallons are entering per second. And we get a total of 400. Okay, so for part C, let's do the following. We'll have one more for this one. Let's consider, finally, let's get the average. So find average volume of gallons. And you could say like in 90 seconds, 90 minutes, whatever our units are, we'll just say from 0 to 90, okay? So T here is from 0 to 90. Okay, well, we just did this, okay? So the average function, the function is giving us the volume, the total number of gallons of something. It could be like oil, it could be milk, it could be anything. And so to find the average volume, this is what you do, okay? You use the average function. And so for us, that's going to be the average here, right, like this, F_av, is 1 over b minus a, okay? Now b minus a are the bounds, it's 1 over 90. So in effect, we're dividing the integral by 90, and the integral here is going from 0 to 90 f dx. Right, this is our function f dx. Okay, now, this is a table, okay? And if you have a table, unlike this one, you don't have a function. This one we could just integrate the function. Up above, oh, it's a derivative, we just go back to the function. But now we have the function itself, we need to integrate this. We can't actually do it because we don't have that kind of information. So what we need to do is approximate. And the way that you approximate is one way is by Riemann sums. So that's what we're going to do. We're going to approximate this integral by taking a bunch of Riemann sums. Now we can make the choice whether we do right-hand or left-hand sums. And that's done in the following way. It's like when we look at the interval from 0 to 10, okay, that has a length, a width, the rectangle of 10 units, but what's the height? Is it 100 or 200? And you can see this function is strictly increasing, and you could even decide in the context if you wanted an overestimate or an underestimate. If you wanted an overestimate, you could take the values to the right, the higher values. If you wanted an underestimate, you could take a value to the left. Okay, it would probably depend on the context of the problem. If you want to make sure you have enough of something, you would want to take a lower bound and go left, so we will do a left. Okay, so we keep the 1 over 90, and then we're going to have a bunch of multiplications. So this will be 10 times 100, because we keep taking the left values. Now it's 10 times 200, plus, and then the next one, 20 times 250, plus, now we got 30 times 100, plus, I think I'm on the last one here, 20 times 400. Okay, so we get 1/90th times what? Well, okay, so we've got 1,000 plus 2,000 is 3,000. Is that right? 3,000 plus 5,000 is 8,000. 8,000 plus 3,000 is 11,000. We get 19,000 here. And so dividing that though by 90, because we're looking for the average, we can take out a 0 and just say it's 1,900 over 9, whatever that is. Okay, so that is how you would get the average value of that function. Now, I want to do one more problem. It's sort of like, these are called like net change problems. And what the heck do I mean by a net change problem? it might be something like this, okay? So you have an acceleration, and you have some function, you know, that gives it to you. Perhaps it's t squared plus 1 times t. And you know, say that the velocity at, I don't know, say it's time 1 is equal to 4, whatever it is, 4 meters per second. And what you want to know is, say, an in velocity, like what's v of 5. Okay, so how do you go about doing a problem like this? Okay, this is called a net change. Let me just write it out like this. Look, if you're looking at acceleration, and you're looking, say, between 2 points, like in this particular case, we could go between these 2 points. We could go between 1 and 5. And we know that the acceleration gives us the velocity, right? So you integrate the acceleration, you get velocity, right? Okay, so and what do you plug in? Well, first you would plug in 5, and then you would plug in 1, right? That's how just regular integration works. You work with the endpoints. But in this particular problem, they give us v of 1 and they only want v of 5, okay? So you add the v of 1 to the other side. We want to find v of 5, so let's write that. V of 5 equals, it's v of 1, it's 4, but we'll just write it in versus v of 1, plus the integral from 1 to 5, and we can plug in our function for a here, which is root t squared plus 1 times t, dt. Okay, so, you know, the point of this example is it's sort of like a new thing that they highlight in AP calculus classes, which is, oh, this is like a net change. And so it simply is kind of like a sort of a simple application of integration if you know how to look at it, which is just that, yeah, like if you want one of the endpoints and they give you 1, you can get it, right? Because you have v of 1 equals 4. And so you just write it out as a regular integral, and, you know, things will fall into place. Okay, so let's do this. So v of 1 is 4. Now what's this integral? Okay, this is interesting. So, you know, a u substitution might be helpful here. In fact, maybe let's go ahead and put up the u substitution. And we can say here u equals t squared plus 1. And then what's du? Du would equal 2t dt. And that's great because you've got the t right there. Okay, very important. And so you have the t dt, but not the 2, and so we can deal with this. Okay, so now let's plug everything in. So v of 5 equals, v of 1 is 4, plus what? We want the integral from what to what? Okay, let's just switch over to u's. So u here would go from, if it's t is 1, that'll become 2, and then 5 squared would be 26. Okay, so now we're in terms of u, and then what I have is just square root of u du, and I still would have this 1/2, right? Because this 1/2 we didn't account for it, so, you know, I left a little room. I'll just stick it out over here. Okay, the 1/2's going to come out in front, and so we continue to say v of 5 equals 4 plus 1/2. Okay, now we integrate u integrate u to the 1/2. You're adding 2. That's 3/2. So it's 2/3 u to the 3/2 evaluated at 26 and 2. Okay, and so what you're left with, v of 5 equals, those two cancel, it's 4 plus 1/3 of, you know, whatever these are, right? So it's 26 to the 3/2 minus 2 to the 3/2. Okay, and that would provide the final result. So this is sort of like a mixture of some different kinds of problems focused on sort of like direct applications of integrals. The mean value theorem is sort of like the main point. Recall that given any sort of curve, you can find a rectangle that has the same area under that curve according to the mean value theorem of integrals. And if you ever ask for the average of a function, you can apply that. If you're ever looking for the net change because you only have one of the endpoints, you can do that here. And so these are also using the fundamental theorem of calculus, which states that the integral, right, is an antiderivative. So integral of acceleration is volume. Here you have, and if you have the integral of a derivative, its antiderivative is the function itself. And you only need to look at the endpoints in these particular cases.